So we decided, okay, we have a solver object which is much smaller, and through this solver object we then pipe all things in via a solve method that gets boundary conditions that mesh and pumps out a solution. Okay then, so thank you very much for having me. Today we want to talk about how and why we decided to make a FEM solver in Rust and what the heck an FEM solver is. So what are we doing? First of all, what are we simulating here? Second of all, how are we doing that? Meaning, what is FEM? I guess that's not public knowledge.
Sorry,
yes.
Please move a little bit to the right.
You're right. Okay, I'm sorry. Yeah, it's rather stupid, thanks. Okay, so second of all, what is FEM?
Transparent mode.
Yeah, sorry. Feature not implemented yet. Yeah, so second, then why are we doing it in Rust? How we did it architecturally and what we learned along the way. Spoiler, we've made some mistakes. And lastly, what we can learn from that. So, who am I? My name is Henrik. I'm a mechanical engineer by trade, but I've basically started to do computer programming at the age of 10-something-ish in Visual Basic 6 and progressed from there, and soon found out that the software computer scientists ended up writing for us mechanical engineers is pretty crappy, and I wanted to do that myself. So I wrote a PhD thesis about doing that and become an expert for simulation software along that journey, which often terrifies me even more on the quality of software, both my own and others. And now I'm the lead developer at Dr. Q, and by the way, I've brought Dennis and Andy from my team, who you can also ask many questions. Okay, so which problem are we solving here? It's getting this image, by the way, in the very end. So what you can here see is a steel pipe welded to some bracket, which is then fastened with a bolt to this plate here. And that's what we want to know is how stressed is the material. Because stress, in the end, leads to deformation and then to cracks. And you don't want to have your car cracking, at least not while you ride in it. And finding this out experimentally is often a pretty costly endeavor, because that means you have to build the thing, you have to build a test stand to do the experiment with, yalla yalla, and all that to find out that you are way off the mark is a stupid thing to do. So simulation software would be cool, however, it's not so trivial to get these numbers. And the first time humanity found no way around doing that was when we decided that sticking a flag into the moon would be a cool idea. And so the idea is from 1930-ish, how to do that mathematically. Yuri Gagarin, by the way. And so the NASA decided we have to actually do this. And tried to run this on computers. Actually, the name computers is a job description. The job of people solving large linear equation systems by hand to get to these results. That's where it comes from. But nowadays we're doing that in software. But how? So given we have a CAD model, a computer can't do much with that, because how can we reason about that? There is a much more intricate explanation to that. By the way, there is a German Wikipedia article called Verschiebungsmethode. If you want to have a comprehensive intro in finite elements, read that. No joke, that will get you through the first 2 theory modules in university on FEM. It's a great article. But we have a FEM CAD model, and from there we want to get to those flashy pictures. So the theory we are building is conservation of energy, because we know that is true, period. The idea is, okay, we know that the external forces acting on that perform work, because we know force times distance is work. And we know that all work done must lead to changes in energy. And if you think of a spring, if you extend that, you increase the amount of energy stored in that spring. So cool, if we could calculate the amount of energy stored in that, we can find out, okay, how much how much work did the force do, and how much corresponding energy is that in our object, and that is an equation we can solve. So you do not want to solve the integral of the energy over the volume of this body. You definitely do not want to do that over the frame of a bike, for example. So to get to an integration problem that you can actually solve, you just cut that into small pieces. We call those elements. Because these elements are shapes that you can actually solve an integral over. And having this energy formulation gets us here, to a linear equation system. To be precise, a sparse linear equation system. So most of the coefficients in here are 0. And that's something we can solve given enough compute power. I know this is jumping through some hoops of belief. If you want to have a more detailed explanation, I'm very happy to give that, but I thought we are not doing 30 minutes on that. So, how do we actually do that in real-life software? This is a competitor's product, which I've taught for about 4 years in university to students, and found out that they actually have pretty much trouble with it because it's doing interesting stuff. Because first of all, you see it's a button hell. And, well, what is that if you look behind it from a computer science perspective? It's a beautiful UI written in C#. Cool. So you wrote a solver to solve a linear equation system of billions of degrees of freedom in C#? No, you didn't. That's code in Fortran 66, aka punch card code. And the thing is, the guys who wrote that are dead. I've been to a conference where I've talked to an employee of a competitor on a specific bug, and he told me, yes, I would love to fix that, but the guy who wrote that died in the 90s in a plane crash. That's over. We can't do that. So this model of writing software is sort of dead. You have to do something because the code in existence has lost maintainability. And that's basically why we want to do a rewrite. There is open source code for that online, but when you look at that, you find interesting stuff too. Because, well, in the end, we are basically here because many things that people say, okay, cool, I want to do that in Rust, but then, okay, no, we have this code. It's been used in so many projects. We are so very sure that it works, but not really, because then you can't really work on it. It's not soft anymore. It just turned into hardware. You can't change that unless you have a hammer. And last of all, we all know that having code which solves many problems is in no shape or form guaranteeing that it has no bugs. It often just means that people have started accepting the bugs. For example, this is not a joke. I found this issue in a competitor's product. It's known to the software manufacturer. He says, I can't change that. What does it do? It produces results in a spreadsheet form if you want to iterate over many construction variants. Thing is, the results are permuted in a random order, so you have no heck of a clue which design variant corresponds to which result. Software support told me, also export the mass, and then you can guess which variant that was. Official solution. So, I don't know. I don't accept that solution, sort of. I thought writing it in Rust would be more fun. And why is writing it in Rust a good idea, at least in my mind? It's a thing about qualification, basically. Because when you want to write a working FEM software, you need to be in classic software land. You need to know three things. You have to be a good engineer who understands the physics at hand. You have to have a pretty good understanding of numerics, And well, you are implementing that in C, so you shouldn't shoot yourself in the foot with a pointer, which will happen inevitably. So I, for example, live here. I know people who live there and there, but I know 0 people who are here. And the thing is, if I use Rust, Rust is great because I am too dumb for C. That's the base of it. I can do it in Rust without shooting myself in the foot and have experts for the little C stuff that we actually need to do that who don't touch the engineering that much. That works. So this is basically the why we did it. And now on the how. So this is the initial architecture we started out with. Spoiler, this is not how things look today. So we basically said, OK, we want our customer to generate a Python script, because Python is what engineers learn at university. And second, the internet is filled with Python, so we can use a large language model and fine-tune that to generate our solver input decks, the code to run it, because they are confident in Python, and teaching it to use our new library is not that different. So that seemed like a smart idea. Then we say, OK, all the hard solver logic, the math stuff that you need to have basically a PhD in to understand it fully, we do that in Rust, because then people can do that who are not versed in C, but know the numerics. And then we have these little fellas, which is, first, we need a solver to solve the linear equation system. And you don't want to do that. We decided to use a library called SuperLU, more on that later. Second, we need that lovely mesh that you saw, made from the geometry. I can tell you, handling CAD geometry via spline objects is a terrifyingly complicated thing that I wish to never do firsthand in software, so you really don't want to do that yourself as well. So these are C libraries we depend on. Looks like something you could do. Let's see how it went. As a more detailed look into the Rust world here, we basically did this. We say, OK, we have a simulation object which holds as its attributes the boundary conditions. That's how do we load that part mechanically. OK, it's held up here, we have a force acting in this direction there of 10 newtons, stuff like that. That's our boundary conditions. It holds the mesh as an attribute, and the equation system solver, and an option on the actual result of it. And the mesh then is the coordinates of the nodes in 3D space, the elements, which is just a giant, basically a giant matrix saying, OK, the first element consists of nodes 9, 5, 6, and 8. And the materials used, because if you do that with rubber, you get different results than with steel. And the solver holds the equation system matrix and the LU decomposition of that. Sounded like a plan. It didn't last, because it turns out if you do that, you are getting multiple problems. First of all, LU. LU is a giant thing. This matrix can easily have tens of gigabytes. If you have that in this object, and then you send this object with Pyo3 to Python, you see where this is going. Second thing, SuperLU is smart. It does very smart things with memory, but things that are A, too smart for the borrow checker to understand, and B, that get Python freaked out as hell, aka segmentation fault guaranteed. So this is pretty unstable. We'll get into that later. So we decided, OK, we do not want that matrix to be in a Python-managed object. Second, the mesh can also become a giant thing. So that can also go into the gigabytes, so also not the best idea on earth. So we decided, OK, we have a solver object, which is much smaller. And through this solver object, we then pipe all things in via a solve method that gets boundary conditions at mesh and pumps out a solution. That's something that worked a lot better. And now in the trouble of integrating stuff. Because this is actually what turned out to be most of the trouble we had, actually. Because we had math issues, I would call them, which were mainly caused by slight misunderstandings, typos in copying papers, stuff like that. But from a software engineering point of view, most of our problems in the solver world are, in the end, interfacing. So what is GMesh? GMesh is a library which creates meshes. It's maintained by two lovely scientists from Belgium who do a great job, but they are electrical engineers and scientists first, and software engineers ninth, maybe. So I'm not a C guy. Daniel is. Sadly, he's not here. But I have seen him grow multiple gray hairs while trying to integrate that better, because my integration of that was sloppy at best. Because from the outside, GMesh looks pretty nice. It only exports functions which use trivial C types. That sounds good. Until you understand, okay, the thing depends on Open Cascade. That's a cat geometry kernel, managing that spline-based geometry I've talked about. This is an actually open source project. It's the only open source cat kernel, so there is no option to use anything else than this. This is maintained by Capgemini. I don't know how to pronounce that properly. So giant French consulting firm. They maintain that to sell projects on that. That's a C++ code base, which consumes 90%-ish of the whole compile time of our complete FEM solver and all its dependencies. That's why we cache the artifact in GitLab. Thanks for Andy for building that. Saves a lot of compile time. And then you have the core of it, which is a giant mess of C code written by dozens of PhD students over decades. None of them were computer scientists. They all wrote C code with one goal inside their mind. I will do the research I have to do. I will hand in my PhD thesis in 4 years max, and then I am gone. Turns out that is not the way to write sustainable software, I guess. What you basically end up with is it has no observable structure. At least that's what Daniel told me. I have to tell you, I have not looked at the code base enough to have a clear picture, but it's basically unchangeable. It survives its own tests, and that's all we know, basically. I wrote my own PhD thesis on meshes by just wrapping around its Python interface and using it from there and extending it from that perspective, because that seemed to be the only viable option. So what we can learn here is, do not estimate from the outer boundary of a library how easy it is to integrate. GMesh, for example, does hellish things with state. What GMesh turned out to be, which it doesn't look like from the outside, is GMesh is basically a command line program which you can drive by, instead of typing commands, using the commands as C methods through a C interface which has an FFI. So GMesh has a state which mutates with every method you call. This state is a static, so it's not thread safe, and it does many funny things. So you have to write a lot of wrapper code to get that in a sustainable state where you can safely work with that. The only way this works is a static log, but it took us about half a year to find that out, because the docs don't say. After a 9-ish month, I found a post on a mailing list. Is GMesh thread safe? The answer by the maintainer, no. End of message. So, okay, now we have a mesh. We have some numerics magic, which gets us a linear equation system. We want to solve that. So that's also a piece of software I can guarantee you do not want to write. Because doing that in sustainable performance is a hellish task. From what I know, SuperLU is the cumulated effort of about 100 PhD students. So what does it do? We have a sparse matrix, like that, and we want to turn that into a product of two matrices, L and U. The cool thing, if we have that, is that we can solve the equation system by solving these two equations. And this is also solving a linear equation system, but it's way easier because we know that this is a lower matrix. You just take the first equation, that's just a linear equation with one variable, easy to solve. Then you can insert that into the second, which then also only has one variable, and so on. That's pretty fast. This is consuming 90+% of computation time. So you can also use that if you have similar problems, which only vary in the right-hand side vector of your equation system, so this thing. You just have your one decomposition and throw in all the right-hand sides, and it's blazingly fast. By the way, all that old FEM solvers can't do that. We now can, which is pretty cool. So why was that written? For this. Basically ICBMs, intercontinental ballistic missiles, and finding out where they hit. So this is as single shot as software gets. And it's written for supercomputers, so a lot of the application boundaries of the cloud universe we live in don't apply there. And that hit us pretty hard and required some effort. To put it mildly, this is how our journey went. I looked for Rust bindings to SuperLU. I found a crate, because SuperLU is basically three things. There is SuperLU sequential, multi-threaded, and MPI. And I found a Rust crate by a nice guy from Sweden for the sequential variant. It was pretty dated, didn't compile on a modern Rust target. I put in some time to fix that, contributed my changes, and it worked. Awesome. And then I thought, okay, the multi-threaded version has a similar public interface in C-World. So I think I'll be looking for some student to translate that for me and be done. I didn't find someone, okay. And then a guy applied who said, well, I'm looking for a new job. I have quite a lot of experience in C. And I said, okay, listen, man, I have this problem currently. Just give me a concept on how you could do that as a proof of work to see if you would be a fit. He looked at that and said, okay, I think I can do that. Gave me a pretty good concept. That was Daniel. Daniel has 30-ish years in C++, and it took him 1 year. So why is that? And by the way, the MPI version we never touched. It's just these two. You have comments, you have docs, and you have codes. They tell three stories, and they do not line up. Not at all. So that's one thing, why it took 1 man year for a super senior C developer to get there. Second, well, how do you think do these guys do error handling? This way, just the ref and null pointer. That's cool, it's sec faults, your program is over. Despite your program is multi-threaded, one thread is over, and the rest is running for I don't know how long. It doesn't matter if you have a supercomputer. You don't pay the energy bills for that, but our customers seem to care. They actually want to know that a simulation has failed. That would be pretty cool. And you also have things like, how much memory do we actually need? Turns out you can't really know that beforehand, so you have to do a rough estimation. But everything that can go wrong will funnel into a segmentation fault by design. And it turns out the internal memory management of that thing is not that blazingly either, because if your memory, if all your error handling is segmentation fault, and you see a segmentation fault, you think, okay, something went wrong, so you can't even see anymore that you have an actually memory bug. which is causing your segmentation fault. We are currently in the preparations of a merge request to the United States of America to give them their code back with some fixes. So Daniel did some fun project over Christmas, which is, okay, we have pretty solid testing for that thing. Just throw that into Codex and wait. Give me a Rust rewrite of that thing. Fun thing is, that actually worked. It passed all integration tests, but it's not the same algorithm. It implemented something that does the same thing on the surface.
Most probably.
Yeah, well, it passes all the tests, so the observable outside behavior is the same, but
How good the test?
yeah, I think our testing for that is pretty good, but performance, well, you can do that, but results are for your grandchildren.
Did Codex have the integration tests in context?
Yes, he gave,
Just adapted to the tests, kind of.
yeah, obviously. The thing is, you have to know, SuperLU does pretty naughty memory stuff. For example, you give it that A matrix, and you would say, okay, it can't really permute that because that's the input, and I get two other objects back. Actually, it can. What it does is, it allocates new memory, which is then moved in a way that it is written in place where the old memory of the A matrix was, and writes the two new matrices in there, which means to date we have no real way of mapping that to Rust borrowing behavior. The only way we currently have is we give it a mutable matrix and have a comment in our code which says, do not touch this matrix after handing it over. It is garbage. It's segfault if you read it. Yeah, but we have one thing that we shouldn't be doing. Yeah, and so Daniel went to strategy 2, and that's actually working, which is pretty funny. So what he's doing now is, I take one function, think of a proper Rust interface for that, and have it rewritten, piece by piece by piece. Good thing is, SuperLU is giant on one hand. On the other hand, the stuff that we actually need is not that big, because we are only interested in 64-bit, we are only interested in real numbers, we are not interested on how to run it on a Cray CPU supercomputer from the 1980s, and so on and so forth. If you reduce all that, you get to something manageable. And we are pretty close to having rewritten SuperLU in pure Rust. Mostly safe. So, and most of that code is actually written by Codex. So if you do that in a controlled environment, it can be pretty good. But don't expect miracles. So I would like to touch a pretty different topic, which is UnitForge. If you are in the world of doing stuffs with physics, Rust gives us type safety, which is great. But as an engineer, I would really appreciate to have quantity safety. I want to know if what I do is physically sound. And I wrote UnitForge to give me that. So I can, for example, say, OK, F is a force of 100 kilonewtons. And then I can output that to a float again, for example. And if I multiply a force by a distance, I get a moment. And if I add a moment to a force, I get a middle finger. The thing is, how do we actually store the data? Because it turns out 64 bits is actually not that much. Because if you are in the world that, for example, you are using your FEM simulation to simulate what continental shelf does if it's hitting each other, there are people doing that. And on the other hand, there are people who do nano-robots in finite elements. And if you scale your numbers for one of these applications, you will lose in the other. So doing that was not a good option. Instead, we decided to craft a data type which is basically what standard engineering notation. A times 10 to the power of x. And that gives us enormous precision, because now we can just use power laws to calculate with that. The only point which we have to care about is you sometimes have to rebalance the power so that the multiplier gets smaller again, so smaller in magnitude, to get back to reasonable numbers. You don't want to do that every time because that involves calculating a logarithm and that's expensive. But if you manage that, you get pretty accurate results. Furthermore, we found out that sometimes you don't know in advance what physical quantity you get, so we also did a dynamic wrapper which uses an enum. I really love fat enums, one of the greatest features in all time in Rust, I think. And that also allows us to do stuff like that. So we now get out what we want, and we can find out if what we do actually works. And we can also use that to have more complex objects, like vector 3. So we implemented a vector 3 because we are in 3D space, and having a vector of length 3 statically is actually a pretty big advantage over just having dynamic vectors. And we can also just leverage Rust type system there. We just have a generic, and it works for everything that you can legally multiply a vector with. So, sounds a bit bloated, I guess, but if you look at that code, you soon see why that could be a good idea. We calculate an inwards normal, then a force vector, and then we do all this shit. And if you want to know whether that's unit consistent, you can think about that for quite a while, and I am in the great place that the compiler tells me, is that working, is it not? My IDE even highlights me, this now is force divided by distance to the fourth, or stuff like that. And I do not have to find that out myself. Awesome stuff. And by the way, all FEM solvers on the market just work on pure floats. So it's up to the user to find out if the unit system he is using is actually consistent and what the numbers he's getting out actually mean unit-wise. That's also something I think is not a good design feature. So UnitForge also has a workable interface with typical Rust crates. It allows PyO3 interfaces, serialization via SerDes, and can be implemented in an arrays. These are optional features. You can get UnitForge at crates.io if you want to use it, if you want to contribute. If you want to contribute, be warned, the only way I found to implement that sanely was a code writing build, or as if that's the smartest way of doing business, I don't know. But I am not an not a syntax tree ninja, so I didn't try that. So where does that get us? Errors in unit conversion do not happen anymore. And actually, these are common and cost a lot of money and get a lot of things broken. For example, the United States of America once tried to send a satellite to observe Mars' atmosphere. Turns out they didn't hit it, because Lockheed Martin made the satellite, NASA programmed the braking thrusters, and was sent a spreadsheet of numbers for the mass distribution and assumed that were pounds. It weren't American pounds, but British pounds, and they missed Mars. So that does matter. Second, as iterated many times, the compiler proves that this is working, and I think as Rustaceans, we all agree that having proven by the compiler that we are right is a good thing, so we're just extending the concept. Floating point precision is basically a thing of the past. You don't have to care about that anymore, and it's a lot more readable, especially if you have an IDE which gives you type highlighting. And yes, there is a performance penalty, but it's minimal, and the only thing where we do not use that is the pure equation system itself. There we don't do that. Everything else is physically typed. Okay, so let's conclude on writing an FEM solver. What I shouldn't do again, maybe. Pros and cons. So it's a lot faster. So we got here in about 7 man-years. Competitors' products needed to get to a similar point, rather 20-ish man-years, often a lot more. And their stability is often questionable. And it's not that they don't have bugs. You find them on a pretty regular basis. Then doing stuff like this in Rust is valuable because, to be honest, runtime errors suck. And to find that out in advance is very valuable. Also, you have to keep in mind what runtime errors in numerics often means. Your result is 20% off. Great. What does that tell you now? You can take a very long time to fix that. In my master's thesis, I wrote an FEM solver, which was not in Rust, and I had an error which turned out a forgotten bracket, which took me, I think, 3 months to find. By the way, UnitForge would have caught that because that made the calculation unit-wise illegal. And then in Rust, you get all the tools you need in one stop. Yes, you can say, OK, I can use this tool in C plus this and that, and then I have this ecosystem which does it also. But it's fractured. Everyone uses different stuff. Every company has its own build chain. And in the Rust universe, everyone agrees on, we do this with cargo, full stop. That's actually pretty valuable, especially talking from an employer's perspective. If I hire someone who has any experience in Rust, I can count on, OK, this guy knows cargo. That's worth quite a lot. If I hire a C guy, I can start a sheet of 50 boxes to match our tech stack, if we were doing that in C. And by having requirements in cargo tomls which are checked, I also get pretty reproducible builds. So compile time is not that great, but as we have seen before, an ancient C++ program dominates our compile time anyway, so not that much of a deal. And we were missing some crates that we would like to have, didn't have, and ended up writing ourselves. So since we made part of that open source, your pain, if you want to follow us, is at least limited a bit. So there are a few things that I thought were a lot less big than that turned out in the end. So it's first, our loved crate universe is a bit fragile when you have a larger dependency list. OK, I want to upgrade to a new Python version. That means I have to upgrade to a new Py 3 version. That influences the NumPy version I can use. That influences the ND array version. That influences the 30 version, and so on and so forth. So finding legal version combinations can take half a workday, which honestly sucks. I think we should find a system which couples less tightly in versions. And, well, interfacing with old code is often hell, but that's, as we've seen, mostly the problem of the code we interface with and not the problem for Rust, but you still have to take into account if I have to FFI to old stuff, it's probably broken. Just estimate it's broken and be surprised if it's not. If you want to find freelancers who work competently in Rust, honestly, don't expect anything. I didn't find anyone. Short answer. I have deep hopes that gatherings like this will change that, but for now, that's basically the case. And there are a few things that I would have not done with hindsight bias. So everything I interface with should be evaluated if I actually want to do that or rewrite the damn thing. I think SuperLU is a perfect example. We have taken 1 year to get it fixed in C, and we are now, I think in full-time equivalent, about 3 weeks in for a full rewrite, and I think we are 70-ish% along the way. Well, having done the interface taught us a lot on how to do that, but anyway, still not worth it. And if you are using code from the university universe, let's call it that, it's often very interesting because you have zero long-term ownership for anything, and you have near zero interest in doing stuff that scales in a software engineering way. And honestly, geometry sucks. Just short, try to avoid working with geometry when you can, because people think that they are good at it. No, you aren't. No one is. Geometry is just insane. So for working with Python, it's actually pretty surprising to me. I would have always thought, okay, Python is object-oriented as hell. I don't know anything which is more object-oriented than Python. So I should have a very object-oriented internal structure to serve that. Actually, the opposite is true. You want to get as functional as possible so that your Python objects become small and easy to handle. And especially if you then interface with C code that might do nasty memory stuff, you might be stuck between a rock and a hard place, because you can't do many things because of the board checker, and you can't do others because of Python, and then you have nowhere to go. And that's also influenced the last point. If you want to do Pyo3 bindings, Pyo3 wants you to do that in a very macro-driven way nowadays, because it looks nice. You have no boilerplate code, but it's not that great of an idea, because the requirements for your internal implementation code and the requirements for your interfaces often are contradictory. So having a abstraction layer often helps in reducing the coupling and gives you the freedom to choose the right solution for both worlds. So far, I'm happy that you wanted to listen to that, and I'm glad to answer questions.
Yeah, thank you very much, Henrik. And I'm happy to open the round of questions, looking into the audience now. There's Tadeo.
Yeah. I have one question. I was wondering, why are meshes used for this finite element method? Because they looked quite regular to me. I was just wondering why it's not done on a more volumetric representation like a voxel grid or something, where you don't need to store so much additional data on all the vertices and connections in between.
Okay. This is a pretty special non-representative representative case. A picture I stole from a dissertation to show something else. So this is much more the real world. So you have very complex geometry, and you have conflicting goals. First, you want your mesh to approximate that geometry as closely as possible. And second, you want your elements to be as close as possible to their original shape. For example, a tetrahedron with equal edge length. And these conflicting goals have to be brought in line with each other. If you do something like a voxel grid, you get elements which are very oddly shaped. That degrades the quality of the differential operator in that. So all your solutions which represent the derivative of your solution, and the stress that we are after is the derivative of the deflection that we are computing, that goes out of the window. And second, you cannot have hanging nodes. Every node must land on other nodes, not somewhere inside a face or on an edge. That also gets pretty complicated very fast.
So all the elements are on the surface and not inside.
It's a full volume,
Yeah.
because we have to calculate the energy over the whole thing.
Yeah.
That's why you also need the internal
Yeah.
structure.
Okay.
You can do only surface elements, but that only works if you have a thin structure like sheet metal, and then do different math to account for the element thickness.
Okay.
Hi. Somewhere in there you mentioned that your current interface is through Python mostly. Are you also planning to have a visual representation like we see on the slide now in not your product? And if so, like, are you doing that? Would you do it? And if so, would you do it in Rust?
No, we do not intend to build a UI. So a classical UI. We have a UI which has 5-ish buttons. So why did we do that? If you look at this product, what this in the end does, you configure your stuff in that UI, and from that it generates basically punch card code and runs that through the solver. Thing is, well, software which generates code from button clicks in other universes tends to not work that well, to be mild. And the reason for that is, and it's also the case here, and the reason for that is you have a giant space of state which you want to describe. So the amount of choices that you might have made with a UI is giant, and that creates multiple problems. First, it's basically untestable. You have near zero test coverage in that UI, which means it explodes everywhere. Second problem, it's invisible. I cannot see what I have configured here, and I have no sane way of searching that. A friend of mine in his dissertation had the problem that in this exact software, he misclicked on which material he wanted to use for a certain part in there. His results were off. The search to find that bug in his configuration was 8 months to find a wrong checkbox. So our main idea is you want to have text because you can actually read and search that, and you can interact with that through an AI system, whereas interacting with an AI system with either punch cards or buttons is close to impossible. Does that satisfy your question?
Yeah, I guess I understand it for the inputs. I was more curious about the outputs, right?
Output is visual.
Okay.
We also create visuals like that.
And how do you do that?
WebGL. So, 3JS. If you want to know more, turn around. Dennis does that.
Yeah, so I wanted to ask about basically, is your product like commercially successful already? And if so, what do customers appreciate perhaps about your product compared to other solutions? Like, is it stability, is it other aspects, and kind of how that then links back to basically your engineering choices?
So commercially successful? Nope. We are on the market, so we are actively trying to sell the product for 5-ish weeks. And we did not do that over Christmas, so nope. But we are starting to get it in the hands of engineers. So first commercial test phase starts Monday with a client. So our main goal is to reduce the required qualification. To be able to use this product, so put it this way, I personally have 7 years of experience in this exact product. I would rate myself maybe an 8 out of 10 on how well I can use that. And I think that's appalling. And that means, as a company, you have multiple problems with that. First, you have to hire experts for that single product. That means you cannot change that product or you fire a whole workforce. You have a small pool of workforce that you can actually hire because you have at least 6 big players on the market who make the software. And it's expensive as hell in the end because this software costs you about 20 grand per year per person. But then you have to pay the guy. You have to pay the computer the guy has, and so on and so forth. And as a small or medium-sized company just can't do that, they say one of two things. Either, fuck it, I'll just pray that it works, build it, and that seems to work because there are only the companies out there for whom it worked, because the others are bankrupt. Yeah, honestly, that's no joke. I once had a client when I worked at university. They made a part for a nuclear power plant that turned out not to work in real life, and produced skull-sized steel splinters. To find that error through this construction error through simulation was an effort of about 3 of my days. So it's not a Herculean effort. It was pretty clear that it doesn't work, but they could do that. And I don't know if it nearly bankrupted them. They're still on the market, but I think it gave them unpleasant talks to their client. So many people who did that are not there anymore to tell the story.
I'm not an expert on that topic, but I think simulating fluids is it somehow comparable to your finite element method? So my question goes into that into the direction whether you plan to expand on those fields, so fluid dynamics and stuff.
So the finite element method is, to its core, a method to solve partial differential equations. So, and the Navier-Stokes equation is a partial differential equation. You can solve it with that. People do. For fluids especially, many people don't use finite elements. They rather use finite volume theory. You can derive finite volume theory as a special case from FEM, if you like, mathematically. You can see it like that. It's a special case of it. The problem in fluid dynamics is if you have a vortex. This vortex must be bigger than the cell it is in. Otherwise, you can't see it anymore, because then it wouldn't produce flow between cells. So there you want to have very, very small elements, but the information you are after is your primary solution. The numbers in your left-hand side vector of your equation system. That's what you want. Here in structural mechanics, we are after a secondary solution. So the derivative of our equation system solution by space, because that's stress. And if you want that, you are highly sensitive to if your elements have a good shape. And that creates different requirements for what you want to do. So we are thinking about expanding into other physics, but the closest choice would be thermal conductivity, because that's more comparable in numerics.
Thank you.
You have so many calculations. How is the GPU support for it?
Pardon?
The GPU support.
Oh, horrible? Just get you to the right slide. So the thing is, if you would do that on a GPU, oops, went too far, not the news. If you want to do it on a GPU, you have to store these 3 matrices in VRAM. They are way too big to be stored in the VRAM of one graphics card. You cannot buy that. So what you end up then doing is you have part of that matrix in RAM or distributed over VRAM of multiple GPUs. So if you're doing that, you are then very tightly coupled, and all you see performance-wise is your machine pumping data through its PCI Express bus. There is a world in which that works, which is a different algorithm. You can solve linear equation, sparse linear equation systems direct, which is this, or iterative. In the iterative method, all you do is you multiply a vector by a matrix very many times. The thing about that is, then you can just take a slice of your matrix, because that's all you need to compute a slice of the output vector, and hand each GPU one of these slices. That's much better, but the algorithm is way slower. So what you do in real life is, you calculate how much memory do I need for this? Do I have a machine which has that memory? And if no, then turn to iterative methods, maybe go to a GPU. But since we are in cloud land, we can just tell Amazon, hey guys, we would like 5 terabytes of RAM, do we have that in shop?
Okay, thanks.
So you talked about one function you rewrote where you handed over some matrix A, and internally the function wrote its outputs into the matrix. I assume the intent of that was to save memory. So are you facing a similar issue?
Well, the issue is to save, mainly to save memory allocate. It's to save memory and to reduce memory allocation calls. So SuperLU has an internal memory management system. They wrote their own malloc to do that, which partially relies on undocumented behavior of the Linux memory allocator, which is also semi-cool, but well. So what these guys did is, their memory allocator moves the memory underlying this matrix into these matrices, and then starts to put stuff in there. That means if I view this matrix after solving, okay. So what happens is the SuperLU memory allocator does an estimation on how much memory he needs for these two matrices. He extends the memory already consumed by this matrix by that, and then starts to write the result into the memory slice it then has. If I then in Rust turn out to access the memory in here, Rust then tries to cast the memory there into types that they no longer belong to, and that usually ends up badly. But I have no way of getting around that, because if I would drop it in Rust, Rust would try to free that, which doesn't end well either.
Just kidding.
So strike was just a warning. Yeah, very nice, very technical. I love when you got this down, that you have to think about memory allocations and stuff, how to do them. Henrik, thank you very much. I would propose we have probably more questions, and Henrik will be around at least till 9 p.m. because otherwise nobody gets home. BVB is playing in 1 hour, and yeah, giving a big hands of applause.
By the way, if you want to have the slides, just ask. You may send them to everyone who's interested.
Yes, we can do that.